Hello guys, welcome to our 8th lecture on our course on photonic devices focusing on optoelectronics. On today's lecture we're going to talk about the probability of occupation, or in other words the Fermi function, which gives us the probability that a given state is occupied by an electron or not. So in conjunction with the density of states, this will allow us to calculate carrier concentrations. Just as a reminder, we saw on our last lecture that using the parabolic approximation, we were able to obtain the density of states in the conduction and valence bands. And these looked something like this. So rho c was 1 over 2 pi squared times m star. And if we're talking about conduction band, this would be the effective mass of an electron, divided by 2h bar squared to the power of 3/2. So multiplied by the square root of E minus the band edge energy. And you had something similar for the valence band, which was rho v was equal, so as a function of energy, of course, was a function of E and was equal to 1 over 2 pi squared. Similar manner, I guess the 2 here goes in the numerator. So times 2m effective mass of holes divided by h bar squared to the power 3/2 times the square root of EV minus E. And these gave us the number of states per unit volume per unit energy, okay, the density of states. So we saw that, for example, in the conduction band, you would have actually, because since you have a non-uniform dependence, in other words, this is not a constant, this depends on energy, that as you go up in energy, the density of states becomes larger, which means that you have more states per unit energy. The states are closer together as you go up in the conduction band, for example. Okay, so you have more states there. The states are more closely packed in terms of energy as you go towards the center of the conduction band. And the valence band, you have the same behavior. But this only gives us the number of states available per unit energy. So you could have, you have states here and here and here, same thing here and here and here, but you don't know if they're occupied by an electron or not. So there could be an electron here or not, or the state could be empty. So to find the actual number of carriers within a range of frequencies, so let's say that we want to know the number of electrons from a given initial energy to a final energy, right here, we need to know the probability that these states will be occupied by electrons or not. So they can be either empty or they can be occupied, and we need to know this to estimate the number of electrons that are actually within a given energy range in the conduction band, for example. Okay, so we need to know the probability of each state being occupied, and this is the Fermi function, or the probability of occupation. And this is the Fermi function right here, okay, a function of energy. So f of E, Fermi function, is equal to 1 over E to the power of the energy minus EF, which we'll see the definition of EF in just a minute, divided by KT, where K is the Boltzmann constant, so 8.617 times 10 to the minus 5 EV per Kelvin, so divided by KT plus 1. Okay, so the Fermi level, EF, is the level for which F of EF is equal to 1/2. So you have 1/2 probability of occupation, or 50% probability of occupation for this particular energy. So this corresponds to the energy for which the probability of occupation is 50%. That's how you define EF. And if you look at this function, it would look something like this, right? So you have f of E as a function of E. Well, if the energy is below the Fermi level, okay, below the Fermi level, this means that this exponent here is going to be negative, okay, and as E is smaller and smaller than EF, it's more negative, so e to the power of a large negative number is approximately zero. It becomes zero as the exponent becomes minus infinity. So you have zero here, so 1 divided by 0 plus 1 is 1. So, okay, for very small energy, let's say very negative energy, Fermi function is equal to 1, and it will have some behavior here. As we saw, for the definition of the Fermi level is that for this particular energy, this would be equal to 1/2. We can check this, so if we substitute E by EF, you'll have EF minus EF, which will be equal to 0. Therefore, e to the power of 0 will be 1, and you'll have 1 divided by 1 plus 1, which is 1/2. So for the Fermi level energy, or Fermi energy, you'll have 1/2. And as you go higher than EF, as E goes higher than EF, what happens is that the exponent is positive and will become larger and larger. So e to the power of a large exponent will be a large number, larger and larger number. So you'll have practically 1 divided by a large number. So which, as the energy goes up, will be closer and closer to 0. So let's say that up here, for very large energy values, you'll have 0. So the Fermi function will be 0. The probability of occupation will be 0. And this is in accordance with what we talk about when we said that the electron tends to stay lowest energy state available, right? If you have let's say, if you're talking about the conduction band, for example, and you have a bunch of electrons at a given temperature, they will not occupy states up here. Most likely, if you have just a few electrons, they will occupy the states at the bottom of the conduction band. So if there are actually electrons in the conduction band, they will be occupying the lowest states available. So the probability of occupation for smaller values of energy is closer to 1, and as you go up, this probability becomes 0. Okay, and at the Fermi level, it's exactly 1/2. So this function could look something like this at room temperature, or if you're talking about 0K, it might look like this, but it will have this behavior. Just by analyzing the function here, you can see this. What else? KT is known, so if you substitute room temperature around 300K here, you'll get a number close to 0.026 eV, or 26 milli-electron volts. Okay, so just a few important facts here. F of E, the Fermi function, is the probability of occupation of electrons, okay, with emphasis on electrons, at the energy level E. This is not the probability of occupation of holes, which is the absence of an electron in a state in the valence band. The probability of occupation of a state by electrons, okay. At energy E naught, F of E naught gives us the probability that the state with energy equal to E naught will be occupied. So this probability can range from 0, which is 0% chance or probability of occupation, up to 1, which is 100% probability of occupation, with everything in between. So let's say if F of E is 1/2, as we saw, this would correspond to 50% chance of occupation. If it's 0.25, it's 25% probability of occupation, okay? And finally, F of E is also called the fermi-dirac distribution. Now that we have the Fermi function, or the probability of occupation, we can calculate the total number of electrons with energies in a given range, right? So as we have been talking about, you have the band structure, and it would be interesting to be able to find out the number of electrons that have energies between a given start energy and a final energy. So energies within any given range, including the entire conduction band or valence band. So from EI to EF, let's say that we want to know the electrons that have these energies. How do we do this? So the number of electrons per unit volume with energies between E and E plus dE. So this is the notation that we're using right here, okay? Let's remind ourselves that all of these quantities are quantities per unit volume, which means that we'll be calculating the number of electrons or the density of states per unit volume, usually per centimeter cubed, which means that we're calculating these quantities, the number of electrons and density of states in a cube of 1 centimeter on its side. So typically that's what we do. So the number of electrons that we'll get will be the number of electrons inside this volume. If we have a larger volume of semiconductor, we can just find out the number of electrons from this. Okay, so the total number of electrons per unit volume in this range will be proportional to the number of states, okay, per unit volume. So of course, the more states you have, right, you have varying density of states. So the more states you have, the more electrons can occupy that given range, of course, because there are more states within the given range to be occupied by electrons. So the larger the number of states, the higher the number of electrons that can occupy that given range. But that's not all there is. If there's a large number of states, but the probability of occupation of those states is very small, there isn't going to be a large chance that there are a lot of electrons within that range. The total number of electrons within that range is also going to be directly proportional to the probability of occupation within that same range. In our previous lecture, we had established that this term right here, the number of states per unit volume per unit energy, if we want to know the number of states with energies between E and E plus dE, this was by definition this quantity right here, okay? Rho of V times dE was just this, the number of states with energies between E and E plus dE. And the second term here on the right-hand side is the Fermi function. The probability of occupation for energy E is F of E. So this product here will give us the total number of electrons within the range. Now, if we want to calculate the number of electrons for a finite range, so notice that there's no dE involved here, the number of electrons per unit volume with energies between E1 and E2, okay, this finite range here, we just integrate the expression that we just saw within that range. So from energy E1 to energy E2. So you integrate rho of E times F of E dE within that range. It is also worth reminding ourselves that the forbidden band between the valence band and the conduction band has a density of states equal to 0. So the density of states for the conduction band was defined for energies above EC, and the density of states for the valence band was defined for E smaller than EV. That means that the range of energies between EV and EC has a density of states equal to 0, right? If you look at the band structure, let's say a direct band gap semiconductor, like we've been illustrating here, this means that this is EC, this is EV, and of course the forbidden band, which is this part right here, has no density of states, or actually has a density of states equal to 0. Therefore, even if the probability of occupation is defined within this region, since there are no states to be occupied, there are not going to be any electrons within this region right here. Now, as we saw at 0 Kelvin, the valence band is completely filled and the conduction band is completely empty in a semiconductor. Therefore, the probability of occupation for every energy level in the valence band must be 1, and for every energy level in the conduction band must be 0, because there's 0 chance of occupation in the conduction band. For an intrinsic semiconductor, the Fermi energy EF is halfway between the valence band and edge and the conduction band edge. So if we plot the band structure, this being the conduction band and this being the valence band. And if this is EC and this is EV, EF is going to be halfway between these two. Now if we look at the Fermi function at 0k, what will it look like? We can try to plot this. So f of E as a function of E. What do we get? So f of E, as we saw, is 1 divided by e to the power of E minus EF divided by KT plus 1, right? So if t is equal to 0, this will be e to the power of infinity, because in the exponent you have a finite number divided by 0. This will give us infinity. Now it can be plus infinity or minus infinity depending on whether E is larger than EF or E is smaller than EF. If E is smaller than EF, the energy E is smaller than EF, then you get a negative infinite number in the numerator of the exponent, and therefore this will give us minus infinity. So e to the minus infinity is equal to 0, and therefore you get 1 for any value of energy smaller than EF. So let's say that this right here is EF, right? So as we said, it will be 1. F of E will be 1 for any value here. Now, by the same logic, t is equal to 0, so this will be plus or minus infinity. For E larger than EF, you'll get a positive number in the numerator, in the exponent. And therefore, it's a positive divided by 0 will give us plus infinity. E to the power of plus infinity will give us plus infinity, irrespective of the energy value. As long as it's larger than EF, this will give us infinity. And therefore 1 over infinity is 0. So as we saw, for any energy value smaller than EF, you get 1. For any energy value larger than EF, you get 0. And you get half right here. So you have kind of a step function like so. So this is what happens at 0k. Now we can superimpose this graph, f of E as a function of energy, to the band diagram. And this is what we get, right? So right here on the horizontal axis, you have f of E as a function of energy which grows upward in the vertical direction. And this corresponds to the Fermi function for t equal to 0k. As you can see, the probability of occupation of every state in the valence band is 1. Therefore, you have a 100% probability of occupation here, and the probability of occupation of every state in the conduction band is 0, in accordance with what we have discussed. What happens at room temperature? So at higher temperatures, such as room temperature, the atoms in the solid vibrate around their central position. Okay, this will translate in a solid being at a given temperature, and the amount of energy associated with this vibration is proportional to temperature. So it's actually proportional to KT. This would be the mean thermal energy, the Boltzmann constant times T, be the mean vibrational energy associated with temperature. And this energy, the energy of the atom's vibration, because we're at room temperature, will be supplied to some electrons which will be able to make the transition from the valence band into the conduction band. Okay, so with this additional energy, there's a small probability that some electrons will gain enough energy to occupy states in the conduction band. So they will not be all in the valence band. A few of them, using the energy that is supplied, from temperature, atoms, vibration, will be able to gain energy and rise up to the conduction band. This process, of course, is a dynamic equilibrium, so we should not be confused. And this is not static. You don't have electrons that are standing still in the conduction band and states that are, always empty in the valence band. At any time, some electrons are gaining energy and some electrons are losing energy, but you have now some chance of finding some electrons in the conduction band and some holes in the valence band. Or, in other words, at room temperature, because of the energy supplied by the atom's vibrations and so on. Some electrons will rise up here, so we'll have some electrons up here. And as they transition to the conduction band, they'll leave behind empty states, which are holes. But the fact that this is a dynamic process means that as time goes on, other electrons will go up and some electrons will go down. And at any given time, you'll have a finite number of electrons up here and a finite number of holes down here, but they will always be changing places, so to speak. Electrons will be gaining energy and electrons will be losing energy dynamically, but the average number of electrons in the conduction band and holes in the valence band is going to remain approximately the same. So at any given time, there will be a finite probability of finding some electrons in the conduction band because they have gained energy from temperature. These electrons leave behind unoccupied states, empty states in the valence band, which are holes, which translate to holes. What we call holes are nothing but these empty states, and holes can move in the lattice inside the solid and contribute to current conduction inside a semiconductor. So of course, if we're looking at the band diagram, perhaps we're plotting this along some given direction, and the holes can move in space. So when we're looking at the Venn diagram, we're looking at energy usually as a function of spatial position, and the holes in the valence band can move around inside the solid. So by plotting the Fermi function for any temperature higher than 0K, for example 300K or room temperature, we see that the transition between the regions where the probability of occupation is 1 or 100% and regions where the probability of occupation is 0, okay, becomes a smooth curve. So if we just take the function itself and plug in any value, positive value of course, because you have positive temperatures, but different than 0 here, you get a smooth curve. What were we talking about when we say a smooth curve? If we plot this, you'll see a curve like this, right? Whereas at 0K it was a step function, now you have a smooth transition between the region corresponding to the valence band and the region corresponding to the conduction band. You have the smooth transition. This will have correspondence with the physical reality. So there's now a small probability that there will be electrons at the bottom of the conduction band. This probability decays with increasing energy. What are we talking about here? So you have right at this position, f of e is no longer 0. So you have a very, very small but different than 0 f of e, and as you go into the conduction band, you have this tail here, so this small value decays to 0 in a smooth way. At the same time, the probability of there being electrons at the top of the valence band decays by a small amount. So some states will be vacant, which correspond to holes. So what does this mean? Well, right at the top of the valence band, this will not be exactly 1. Let's say it's 0.98, 98% or 99%, or even larger, but smaller than 1, which means that you have a very large probability of finding electrons here, but you have the complementary probability of finding empty states or holes, which corresponds to the distance between the red curve and the dashed line here. This part right here, this interval here is the probability that the states are unoccupied or that the states correspond to holes. We'll go further into this discussion on the second half of this lecture.